So by the end of today, we're going to be able to apply our knowledge of slope to things like velocity. So, one of the ways in which calculus comes into the real world is when you're looking at the rate of change of, for instance, the position of somebody relative to time, which is one way the way we measure that is referred to as velocity. So let's see what that looks like. The IROC of the position function, so a function that gives you where you are from a distance from some point, right? The IROC of that particular function is a measure of velocity, right? The IROC of that is velocity. So that's what we're going to be looking at today as we go through this. What I've done is I've given you a function that the S of t, all right, that's the distance from some point based on time, is equal to 2t squared. And what I've actually done also is I put a little graph there to show you the red line represents the 2t squared, starting at 0. Obviously, you don't have negative time. So starting at 0, that function is, let me just make sure I'm monitoring the chat at the same time. That function is rising as you go from left to right. And I'm asking for the velocity at the following time, when t is equal to 3. And what I've done to kind of suggest to you what we need to do is I put a tangent line, that's the green line, which is actually touching the function when t is equal to 3. So let me just circle that very quickly to show you what I'm talking about. It's this point right here. All right, well, that's not a circle, that's a dot. At any rate, so it's that point right there. And we're asking what is essentially the slope of that line. That line is a tangent line that's just touching that graph, that red graph, that graph that represents position. So remember, time is measured on one axis and distance from some point is measured on the other. So as time is passing, at 1 second, this is where you are. Let me circle a few points here. At 1 second, this is how far you are. At 2 seconds, this is how far you are. So these are all distance points. The y-axis is measuring distance at any point in time, right? And the slope of that at any particular point is what we're going to be calling velocity. The rate of change of position relative to time is velocity. It's really how fast that person is changing their position. So we want to know what that velocity is when t is equal to 3. Now, let me remind you that what we said in the last class was that this could be done by using the IROC formula, right? Where we first of all figure out what the function was at 3. So let's figure out what the f of 3, the s of 3 is. Let me go back to black here. So the s of 3 would obviously be equal to 2 times 3 squared, and that's obviously 9 times 2, which is 18. So you're 18 meters away from some point at 3 seconds. Okay, that's all that is really. Okay, so now we said, okay, let us use that a plus h formula that we learned a few days ago, right? Put everything over h, remember? And what we said was we're going to take this function and put a plus h, in this case 3 plus h, in for t. So it's 2 times 3 plus h squared, all right? And that's the whole formula right there. That there's no other t in the function. And then we're going to minus from that the 18, which is the value of the function at 3. And then we're going to divide that by h at the end. All right, this should all look familiar to you. We did all of this last week, Friday. So let's just continue. All right, so that is equal to 2. Now, at some point, you should be able to do this without going through a lot of steps, right? I'm saying that the first term, when you're squaring a binomial like 3 plus h, it's the first term squared, which is 9. The product of these two, which is 3h doubled, which is plus 6h, and then plus the last term squared, so that's plus 8 squared. And all of that minus 18 divided by h. Again, nothing new here. We did this on Friday. All right, so let's see if we can go a little further than that. So that would be equal to 18 minus 12h. Sorry, not minus, that's plus. plus 12h. I know somebody was going to point that out to me because I know you guys are on top of things. So somebody's going to point that out to me at some point. So anyway, 18 plus 12h plus 2h squared minus 18, all of that over h. Let me move this down so we have some more space. And then the 18s, of course, will cancel each other out. So we're left with 2h squared plus 12h over h. And we're going to be asking the question, what is the limit? And I don't always put this in on the side, and perhaps I should, to be perfectly, I just want to make sure that what we're doing is clear. We're going to be asking, what's the limit as h approaches 0 for this function? Well, we can't just plug 0 into this because that will be undefined. We learned this last week. But what we can do is we can certainly factor out, in the case of this, the 2h, and that would give us h plus 6, excuse me, and then we're going to divide that by h, and of course that would mean that the h's would cancel out, and what we're left with is 2 times h plus 6. H plus 6. Okay, what did I do wrong now? Somebody is about to point something out. Who is that? Oh, I thought there was a hand going up. No, maybe not. Is that lm plus h, lm plus h, lm plus h, as h approaches 0? Limit plus h. No, it's the limit as h approaches 0, and I left out the as h approaches 0 part. I'm sorry about that. Okay, anyway, so when the h's cancel out, let's just extend that a bit. Let's bring this down some more. We get to the interpretation in a few minutes. What we need to ask now is, what's the limit? And again, let me move this aside here. Actually, I can't separate it anymore, so I'll just erase this. What we're asking is, what is the limit as h approaches 0 in this case? Well, what we're left with is, of course, 12. All right, thank you, Alexander, 12. So what does that 12 actually mean, right? Let's go back and, oh, I see that I've really messed up the question because I did all of this stuff down here. All right, I'm going to try to pull this back up here. Give me 1 second. Yeah. Unfortunately, I should have, anyway, let's just interpret the answer. So Alexander is saying that the answer is 12, and he's right? And what the question is asking is to interpret this, right? How do we interpret this 12? What does this 12 actually mean in the context of this question, right? Could somebody help me out and tell me what this 12 actually means? I'm not spinning the wheel yet. Oh, by the way, yeah, there is the wheel. We got the wheel standing by ready to go, but not yet. What does it mean? What does that 12, are there any units for that 12? What does that 12 actually mean? Can we start with units? It's 12 over 3, you're saying, like the speed. Okay, yeah, but what units would make sense for this? Stephen, yeah, go ahead, Stephen. I would think it would be 12 meters per second. If we go back to what the question was telling us, it's actually centimeters. But the question was telling us that units are in centimeters and seconds. So this S here represents the distance in centimeters from some point. So when we get an answer of 12 as a rate of change, it's measuring how many centimeters at the 3-second mark you are moving per second. So this really, first of all, right? So let me give you an interest. Thank you, Stephen. You're certainly on the right track back in physics. Yeah, Danny is saying this is absolutely physics. So it should have been centimeters, but Stephen understands that it should have been centimeters rather than meters. So this interpretation should be that this object, is it, what do they call it? Object? Yeah, object's position. So this object at 3 seconds, at the 3-second mark, and remember that this velocity is changing. At 3 seconds is moving at a velocity of 12 centimeters per second, right? So at that point, now, does that velocity change as we go along? Well, from the graph, you can probably tell that at the 1 second mark. In fact, let me ask that question. Would you expect the velocity, just looking at the graph, and I circled the 1 and I circled the 2 there, would you expect the velocity at the 1 to be higher or lower than at the 3 second mark? What do you think is happening to the velocity of this particular object? Is it speeding up, slowing down? What's going on with this object? Based on those two relative points to the 3 second mark. Look at the 1 second mark, look at the 2 second mark. Velocity is increasing exponentially. Well, I don't know if it's exponential, C, but maybe. But the fact is that it is increasing, right? So there is what we'd call acceleration or speeding up. Thank you very much, Danny. Yes, you're quite right. If we were to do the same operation again, but with 1 second rather than 3 seconds, I guarantee, and you can do this on your own time, I guarantee you that that number that you're going to get, that IROC you're going to get, is going to be a lower number, a smaller number than what we have at 3. And if you went even higher up in terms of time, 5 seconds, 10 seconds, whatever, you would find that that would also give you higher and higher velocities, because the slope of this line, which is what the IROC is, which is what velocity is when you're putting this in the context of a distance equation, is getting steeper and steeper and steeper. The steeper the line is, right, is the faster this thing is moving. That's basically how we should be understanding this. Yes, Danny, please go ahead. Yeah. Centimeters, because the question did specify centimeters in the unit. So it's centimeters and seconds. So the distance is measured in centimeters. And I'm just realizing that on my graph, when I label my graph, and you should always label your graphs, by the way, I actually put meters on the y-axis. I should have put centimeters. Anyway, let's move on. All right, so you're welcome. So everybody good with that so far, hopefully. And by the way, did anybody enter the room after I did attendance? Is there anybody who was late and therefore needs me to know that they are here but were not marked present? Because I did mark 2 people absent. Okay, it doesn't seem that that is the case. So I'm gonna move on here. I'm gonna move on. All right. So that was problem A. Let's get to problem B. So this time the object's position is given by the equation S of t, which is, looks like it's a straight line. Y equals 5t, right? So if you think about straight lines, it has a slope and it has a y-intercept. In this case, y-intercept is 0. Doesn't mean it doesn't have an intercept. This does have an intercept. The intercept just happens to be 0. So if the units are in centimeters and seconds, again, determine the velocity of the following time. So we're using the same time, right? The same time at 3 seconds. Now, if I just threw this out to you and said, look at the graph, which is a straight line. If I just asked you, well, what would you expect the velocity to be at the 3 second mark? How would you answer that? Anybody, right? I'm asking the question. Looking at the way this line is, the line for this particular function looks, what would you expect the velocity to be at the 3 second mark? And Taj is thinking 5 centimeters, and Tomalaya thinks the same thing, 5 centimeters. Really? Is that what you think? And Adam and, okay, so Danny thinks 15 and so. Some of my people are thinking something else. Interesting. And Alexander as well. So there's some 5 second answers and there's some 15 second answers. And Danny is having a rethink of this, and Stephen says he's back. Yeah, go ahead. Oh no. Yeah, but and the graph is. I know this says meters, and that's my. Sorry, it should have been centimeters. Okay, but be that as it may. Be that as it may. So let's say centimeters. But I'm still asking, what is the velocity at the 3 second mark? I'm not asking for the distance away from the start. All right, that's one thing. What I'm asking is, what is the velocity at the 3-second mark? That's what I'm asking. So Stephen, who was the last person who put an answer in, is thinking it's 5 seconds, but a bunch of you think 15, and a bunch of you also thought 5 seconds. So which one is it? Or is it neither of you got it right? Right? Well, let's find out. And we'll talk about why the answer is what it is once we've done our calculation. But, and we're going to do the same thing we've always done, right? We're first of all going to find the S of 3. S of 3 is 15, right? So it's, in fact, let me put it in long form. S of 3 would be 5 times 3. I don't know why I put that there. Hold on. S of 3 would be 5 times 3, which is 15. So we know that this person would be 15 seconds away. That's all we know so far, right? So Adam is thinking, is it 1? Or did I do something wrong? We're going to find out. We're going to find out, right? Let's keep going here. So if that's the case, we're going to do what we've always done, which is we're going to find the limit. Bring us a little bit closer. We're going to find the limit as h approaches 0. Put everything over h as usual. We're going to say the 5 times 3 plus h, right? So we're just putting the 3 plus h into the formula, and we're going to minus the 15 from that. Everything is consistent with what we've always done, right? And then we're going to say, okay, so that's the limit as h approaches 0 of 15 plus 5h minus 15 over h. Nothing new that I've done here so far. Everything is exactly as I've done it before. So now this part, of course, I'll just save some space here and put this as being equal to 5h over h. So guess what? As limit as h approaches 0, I'm sure we would understand that this cancels out. And the answer is just simply equal to 5. Huh. And by the way, the answer is still in centimeters per second. And did you notice that there was no h in here at all? The h was gone, and the only thing that came out was 5. Did you notice that? All right. So what is this telling us then in this particular situation where the line is a straight line? Should have stuck with your original answer. Couldn't we have gone back to our root and done rise over run to get the slope, to get the, well, yeah, because what Fernando is actually probably noticing now is what, right? If it's a straight line, right? What do you think should really represent the velocity? Right? If it's a straight line, what is it equivalent to? What should the velocity be equivalent to for a straight line? It's the slope of the line. And it's the same for all points. Now, if you compare that to this graph, does this graph have the same slope everywhere? The IROC, just think of the IROC now. Let me get rid of all of this stuff here. Is the IROC, so think about a straight line. So if the line was, let's say, for instance, here, right? Is that the same slope as if the line is up here? Wouldn't you accept that the slope is changing on a quadratic function, right? As opposed to a straight line where the slope is constant, right? A straight line doesn't change its slope unless it's one of these things where you have a piecewise function, where there's one line here that represents up to a certain point and another line represents. No, in a straight line, it has the same slope everywhere. If it's linear, it remains, that's exactly right, Kushi. That's exactly right. The slope of a straight line does not change. The slope of a straight line is constant. What does that tell you about this motion? It tells you that this object, and I don't know why I'm using lines for that, this object, I'll just write it here. I'll erase that later on. This object is moving at a constant velocity of 5 centimeters per second. Because that's the nature of a straight line. Right? It's neither speeding up nor slowing down. Let me quickly get rid of these two things here that are not supposed to be there. Right? It's basically a straight line, and a straight line has a constant slope as opposed to a curve, as opposed to a quadratic or a cubic or any of the other functions that we've looked at. It has a constant slope. A constant slope, if you're looking at it in the context of time and distance, means it has a constant velocity. It's like you put a car on the road and that car is just moving at the same speed all the way, 5 centimeters per. If you look at the speedometer, it's not changing. It's just staying there on that one speed of 5 centimeters per second. That's only for linear though. If this was not linear, then that would not be the case. So I just wanted to make sure we got that clear in our minds. The fact is that whatever number you put into this function, whether it was 3 or 7 or 8 or 52, that answer would still be 5 centimeters per second. Just think about it. Whatever number I put into the function here, okay, when I put in 3, if I put in 4, then I'd have said 5 times 4, which is 20, but that's minusing 20 over here. And that's why that is going to give you the same result every single time for linear functions. Okay? All right. I like to check in from time to time. So you know I'm going to be calling out people. So where's Richard? Richard, are you there? Richard, where's Richard? Where is Richard? Richard going once. There you go, Richard. You got to stay with me, everybody. Okay, that takes care of that. Let's move on. So is there another way that we could come up with this IROC, right? So what we did on Friday is we used this method, right? This one that's here. So we took f of a plus h minus f of a, and we put that over h, and then we found the limit as h approaches 0. That's okay. All right. And Alicia, you said you're okay, that's fine. All right, okay, Richard. But there's another way that we could do this, which still is a slope calculation. What if we decided to put the function itself, f of x, and I'm circling it right now, then we minused a particular y value of the function, so f of a, then put that over an x which you put into the function, right? So that's your x value. Remember, the first two here are your, one is your y and one is your x. So this is like your y here, this is like your x here. So this is the function itself. F of x is just simply the function. Whatever the function is, just put the function in. And this is the x value that you put in. So the generic x, so it's not like it's a specific value of x. But then what you're doing is you're subtracting from the function itself a particular y value, which is we're calling the f of a. And then on the bottom of that, we're going to subtract that particular x value from the x. And we're going to ask a different question now. Not is as h approaches infinity, sorry, as h approaches 0, just how we asked it the first time. We're going to say as x approaches a. So as the x value that you're using gets closer and closer to a. And I know that that might sound a little bit abstract until we actually do one. But I will tell you that later on, you're going to have a problem set question which actually uses this approach to figuring it out, right? So this second approach, this new thing that we're learning now, wasn't x minus a in the form of 4? Not really, because what we did is we took the h plus a, and then we subtracted h from it. So now, in a sense, we're saying what's we're just taking x generally, and you'll see what I mean in a second, right? We're just taking because the f of x here just refers to the function itself. The x refers to a generic x, a variable, and you see how that comes up as we do the first. I'm sorry, I mean it was x equal to a. Yeah. So before we're saying when h is 0, And it's kind of the same thing by saying as x approaches a. So in other words, as the x value gets closer and closer to a, then it means that that h is really getting closer and closer to 0. So it's really another, in a sense, Kushi, you're right. In a sense, it's the same idea of measuring the slope using the slope formulas. In a sense, you'll see that. So let's get to the first example. Let's see how this works. All right. So now we're using another quadratic function to represent the position of the object. And we're going to use a different t value this time, and the t now is equal to 4. Assume the units again are in centimeters and seconds. So yes, we still, and let me just go back and show you again. We do need to know the function value at the point at which you're measuring the slope, the IROC, and we need to know what the x value is that we're interested in. So that's what the a at the bottom is. So we still have to ask the question, what is the s of 4? So that's not changing. So the s of 4 is going to be equal to 3 times 4 squared plus 10, which, let me see if I can do this in my head. That should be 416 times 3 is 48. I'm going to say 58, but you guys are the ones with the calculator. I'm doing this in my head. Oh, thank you, Alexander. Yeah. So that's what the S of 4 is. All right. So here's what we're going to do. We're going to say now the limit as x approaches a, and a in this case is the 4, by the way, of, right? And on the top, we're going to put the function itself, which is the 3t. Actually, I shouldn't say x, it should be t. Let me change that to t. Let's be consistent with our variables here. So 3t squared plus 10, all right, 3t squared, that is, plus 10, which is the function itself. We're not putting the a plus h into the function. We're just going to use the function itself. So 3t squared plus 10 minus, yes, the 58, right? That's the y value at 4, divided by t minus 4. Okay? So hopefully that is consistent with what I showed you as the formula before. Let me go back and show you again. F of x is this thing here. What is the actual form? What is the actual function? And it is simply the x. In our case, it's t, but just a different letter. So 3t squared plus 10, that's your function. We're not substituting anything into it. We're just putting the function itself. Then minus the 58 divided by t minus 4. Okay, well, so that's going to be the limit. Am I still on black? No? Okay. So that's going to be the limit as t approaches 4 for, just put that denominator back, 3t squared minus 48. Okay? 3t squared minus 48. Well, we can't just simply, many times when we're doing limits, and we're going to be doing limits in the second half of the class today, many times when we're doing limits, we just throw that number in that we're trying to find the limit at. So just plug in the 4. Well, that's not going to work. That's clearly not going to work because putting 4 into this is going to cause a problem. We're going to get 0 as our denominator. So it's very similar to the one we did before, right? So I'm not going to throw that 4 in because I'm going to end up with something that's undefined. So any suggestions as to how we might be able to sort this out? Are there any suggestions as to how we might be able to solve this, folks? Right? We can't just put 4. It says t approaches 4. If I put 4 into this, then the denominator becomes 0. So we can factor out 3 out of the numerator. Okay. Well, we'll do that then. We'll do that. So the limit as t approaches 4, and by the way, well done to Jordan and Kushi on that. Let's factor out that 3. Let's see if that helps us out. So 3, and then t squared minus 16. And then we got the t minus 4 at the bottom as usual. All right, so that's good. Well, that still doesn't help us too much. Difference, oh, thank you, Richard. Difference of squares. Okay, so let's try that. So let's see now. Let's change that to limit as t approaches 4, 3t minus 4, t plus 4. That's how we would factor a difference of squares over t minus 4. Okay. All right. Okay. And then, okay. Thank you, Kush. Okay, good. So let's try that. So we'll do that. So what we really seem to be left with then, and that's good that the denominator drops out. What we're really left with then is 3t plus 4. All right, that's what we're left with. So now we can ask the question of what happens as t approaches 4, because we can actually put 4 into the function this time, right? That would be equal to the limit as t approaches 4 would just simply be 3, sorry, don't need that, would just simply be 3 times 4 plus 4, which of course is equal to 24. And that 24 again is measured in centimeters per second. So quite a good speed there for this particular object. No, that's a different. So let's just go through the steps again. Let's just go through the steps again. I want to be clear. I want to make sure everybody understands what we did. Difference between what we're doing now and what we did before. We're taking the whole function, the 3t squared plus 10, that's this thing right here, plugging that in as our f of x. That is the function. We're minusing the value of the function at the point that we want to find the IROC, which is 58. We worked that out on the line up here before. And we put that over the t minus the x value, or the t value, I should say, for the point that we are working with. And we work that through. But we're going to get to a point where we're asking as t approaches 4, but we can't just throw that 4 in there, because that would you need a therefore statement? You know what, Danny? Yes, and I don't have a lot of room for that, so I put that at the end because I want to answer one more question. What is the average velocity of over the object's first 4 seconds? So I put both of those in as well. I put both statements in after we answer this question. So Danny's right. When you're doing a word problem, you should have some kind of a statement. We'll be using the old formula with as h equals to 0, or using the same. They're interchangeable, but I'm saying that you're going to find, I think, the second one more useful, especially when we get to we'll see. There's a question that's coming up on an assignment. You don't have an assignment, a problem set for this unit, but there will be one for the second unit. There's a question on there which definitely could use that second approach, and I think some of you actually find the second approach easier. That's what I think anyway. But they're both interchangeable. We can use either one. Okay, what's the average velocity of the object's first 4 seconds? So what we're asking is, from the time that this thing started at 0 and until it got to the 4-second mark, what's the average velocity? The average velocity. So this is an AROC question. So think back to AROC now and tell me how I would find that average rate of change, right? So we're looking for the AROC this time. What is the AROC? Can anybody suggest how that's still a slope calculation, by the way. That is still a slope calculation. I don't have a graph to show you for that, right? But how would that work? Well, let me remind you. It's really going to be a y2 minus y1 over x2 minus x1 calculation. That's really all it is, right? We need to know what is the value of the function at 0 and what's the value of the function at 4, and then just simply do a slope between those 2 points, right? We're going to use a secant approach this time, right? When the function starts, and hopefully I don't have to spend a lot of time on this, and it will be obvious what some of these answers are. Y2 would be the value of the function at the end, which we already worked out to be 58, minus what was the value of the function at the beginning? Well, that's just plugging in 0 into the function. And 0 into the function gives us 10. Hopefully that makes sense, right? Just putting 0 into the 3t squared plus 10 gives us 10. So minus 10 divided by what value gives us the 58? Well, it was 4 seconds. Minus what value gives us the 10? Well, you answer that question. What value of x did I put in to get the 10? Right? Put in 0, absolutely. So that works out to be, what is that? 48 over 4. And in my world, that's equal to 12 centimeters per second. So one of the things, thank you, Danny. So one of the things that we're noticing is that whereas the IROC, so the velocity at the 4-second mark was 24 centimeters per second. When we started off at 0 seconds, it was 12 centimeters per second. Clearly, it has sped up. It has increased in velocity. So Danny mentioned a good point. We should put statements. So initially, let's answer it this way. Initially, this is at 0 seconds. At 0 seconds, the velocity. No, I don't want to say initially. I want to say no. Let me change how I'm saying that. Let's answer both questions. The velocity at the 4-second mark. I'll just do that. The velocity at 4 seconds is, I think it was 24. Yeah, is 24 centimeters per second. The average velocity over the first 4 seconds over, therefore, oh, thank you. Okay. Is it okay if I just put 3 dots, Danny? Can you live with that? All right, 3 little dots there. We can hopefully live with just the 3 little dots to represent the therefore. Right, okay, great, thanks. Average velocity over the first 4, meaning from 0 to 4. Is 24. No, 12, sorry. 12 centimeters per second. So the average over the first 4 seconds is 12, and then by the time you get to the 4th second, you're up to 24. Clearly, this thing is actually speeding up. Okay, accelerating. And we're going to spend more time on acceleration and all of that stuff in a future class. Okay, this question actually comes from the textbook. Let's see how we do with this. And we're introducing square roots into this. Total cost in dollars of manufacturing X calculated is given by, and they give you a function, it's a square root function. What is the total cost of manufacturing 100 calculators? So this is not a velocity question, but it still belongs in this section, right? Because we're taking the model of what's happening in the world, in the real world, and applying a rate concept to it, right? And okay, so the first part of the question is what's the cost of manufacturing 100 calculators? Remember, this formula, this model says that the cost is given by this equation. Then they're asking in part B, what's the rate of change in the total cost with respect to the number of calculators being produced when X is 100? Okay. So one of these is not a rate calculation. One is just asking what's the cost? How much does it cost to make 100 calculators? Well, that's just simply doing what? What do we do to get the cost of getting 100 calculators? What do you think, folks? What do I do to figure it out for 100 calculators? Just set X, thank you, Kushi, just set X as 100. So I'm actually working out the C of 100 calculators, right? That's all I'm doing. So that's equal to 10 times the square root of 100 plus 1,000. Okay, just plug, thank you, Ashvan. Just plug, and Adam and everybody else. Just simply plug that 100 into the function. So by my quick math, I'm getting 10 times 10, which is 100 plus 1,000, so that's 1,100. 1,100, what is this, calculators. Right? And if you can confirm that would be great. That's what I'm getting when I plug 100 in. So let me just double check that. 10 times 10, 100 plus. Yeah, that should be right. 1,100 calculators. Great. Thank you. Thank you all. Okay. Quick check-in here. Right? I'm always going to be doing this. Tomaleo, how about you? Does that sound about right to you? Are you there with us? Perfect. Okay, that was a quick yes. That's good. That's good. Okay. So now we get to the rate of change part of it. That's the part that's a little bit more work. And I'm going to use the second approach this time that we did just now. We're going to put the function in, not the a plus h that we did before. We're just going to put the function in this time. And then we're going to subtract the function at a particular point and all that good stuff. So we're going to be looking at the limit as is in terms of x. Okay, so as x approaches 100 is what we're going to be doing. So here's our function. We're going to put the x minus 100 at the bottom, right? Kind of what we did the last time. And then we're going to put the function, which is the 10 square root of x plus 1,000, right? Minus, remember now, the f of the function, or c in this case, the c of the function at 100, which we just did on the first step, which is 1,100. Okay, that's what we did on the first step. So we're subtracting that from it. So let's simplify this a little bit. So it would be 10 root x. Now that plus 100, sorry, plus 1,000 minus 1,100 looks to me like we're getting minus 100 to me. Okay, all of that over x minus 100. And again, I'm going to be asking what's the limit as x approaches 100. Okay, does that make sense so far? Are we good to go? Taj, what do you say? How about you, Taj? Where's Taj? Oh, there he is. Okay, perfect, perfect, perfect. Okay, great, great, great. Okay, but we can't just put 100 into this. We already knew that from the last question. We can't do that. I see that we could factor, but does that help us out? I'm not so sure. Right? I don't think factor is going to help us out much this time. So I'm stuck. And when you help me out, I'm kind of not so sure. I'm here scratching my head. I don't really know what to do. All right, I'm stuck here, folks. Can you help? So Adam is thinking, okay, and Sarah and Taj and a whole bunch of people are saying, how about that conjugate thing we learned last week, right? How about if we try to rationalize the the numerator, right? That might be useful. So why don't we do that? Let's try that. Let's multiply the top and the bottom by this conjugate. And the conjugate in this case would be the 10 root x plus 100 and 10 root x plus 100. Okay? 10 root x plus 100. Thank you, Kushi. Excellent. So that's my conjugate right there. All right, so let me think this through now. The top, remember, is going to become the square of the two terms. So the thing I'm circling here, I'm going to square both of those terms and put a subtraction sign between them. So if I square the first one, I'm going to get 100x, right? Square the 10, I get 100. Square the root of x, I get x minus, well, that's going to be a big number. It's going to be 10000. Okay? So 100x minus, what is that? 10,000. All right? The bottom, I'm going to leave it in factored form. So I'm going to have x minus 100 multiplied by this conjugate that we just talked about, 10 root x plus 100. Folks, I'm just going to tell you again that I am quite happy to slow things down, stop, rewind at any point that something I'm doing isn't sticking with you. Sarah, how about you? Are we good so far, Sarah, with this? Where's Sarah? Sarah, there you go. Oh, no, Sarah, you're the one I was calling was the one who just answered. Sarah, perfect. Thank you, Sarah. Okay. So I'm still kind of stuck here, right? Can anybody suggest? Okay. I'm still kind of stuck here. I don't really know because I still have this x minus 100. I'm going to put a bracket around this, by the way, right? Because it's all of that times all of this. So I'm still not so sure what to do here. Can anybody help me out? Yeah, your teacher is stuck again. He's just factor the top. Oh, okay. Let's try that. Let's try the top. So you're saying factor the top. So I guess the common factor there would, oh, by the way, limit as x approaches 100. So I'm going to factor out the 100. That looks like the common factor there. That looks like it's going to be x minus 100. That looks like what it's going to be over x minus 100 in one bracket. And the other bracket would be the 10 root x plus 100. Okay, factor the numerator. So we've done that. Factor the top. Okay, a lot of you were, thank you, Kushi and Taja and Jessica. That sounded like a lot of sense. Okay, so first we're going to find the limit as x approaches 100. Right, I keep forgetting to put this little piece on the side right here. And how is that helping us though? How does that help us out? Cancel out. Okay, thank you. All right. It's a good thing you guys are here because I would be stuck. I wouldn't know what to do. So that goes with that. So it looks like what we're left with is the following. The limit as x approaches x approaches 100 for 100 on top over 10 root x plus 100. That looks like what's left over. Thank you, Ashvan, Kushi, and Sarah. All good answers. Now, I could actually factor this again, but let's just leave it as it is. All right. I'm not sure if factoring is going to really help us. We could factor this again, just so we know. We could factor out 10 out of the denominator and it would cancel into the top. So we can do that. But let's just go ahead now and because we can put 100 into this, right? That's not going to cause a problem. So let's find now the limit as x approaches 100 for 100 over, we're just going to plug in the 100 into that, 10 square root 100 plus 100. Okay, and before Alexander, I was going to say before Alexander, but he beat us to the punch. He's always on top of things there. So I'm getting 10 over 200, sorry, not 10, 100 over 200, which of course is simply 0.5. Okay, so the limit as x approaches 100 is 0.5. Now, let's put some units on this, right? If we go back, we look at it says the rate of change in the cost with respect to the number of calculators being produced. So, I don't know. What kind of units would make sense in this case, right? I have a half of what? And I mean, every time it's a rate, it means it's this per that. So what kind of units would make sense here, right? What were we actually measuring the x in, and what were we measuring the c in? Because that should be a clue as to what this is all about, right? So look at what Adam put into the chat. Remember, the top represents the thing that we're measuring, which is cost. The bottom is your y over your x. That's what slope is. The slope here is the cost per the whatever the x value is, right? So it's dollars per calculator. So it's really 50 cents per calculator is really what this is. Per calculator. So the cost, let me put this in a statement before anybody, and I'll put the therefore there, Danny. Don't jump on that. I'm going to deal with it. So the rate of change at the $100, at producing a 100th calculator. So at 100 calculators, the cost, therefore at the 100 calculators, the cost is rising at 50 cents per calculator. Okay, there we go. 50 cents per calculator. That's the rate at which, that's what it's costing per calculator at that point, 50 cents per calculator. Okay, I think that was the last question. Let's just make sure. Yeah, so here's our success criteria.